This project developed an understanding of unmanned autonomous vehicles and the programming and control of a jetbot. Our team of 3 aspiring engineers, Jaron, Grayson, and Grace, worked together to combine 6 objectives that we explored during the ME435 UAV module to simulate an autonomous driving system that could select and execute a desired path.
According to Renub Research, the autonomous vehicle market will be a $186 billion industry by 2030. With the anticipated growth of technology in the autonomous vehicle world, cars driving themselves will become a reality within our lifetimes.
As engineers, it's really important that we recognize the abilities of this technology and its shortcomings in the case that we were to work on its development. As consumers, it's important to understand the technology on a higher level so that we feel safe on the roads when we're in the presence of these vehicles. Our learning experience with UAVs was on a smaller scale with the jetbot, but it has applications to this real-world practice.
The team used the 6 concepts explored in the UAV labs to develop an autonomous driving system. The system determines the shortest path between the jetbot and a selected end location. After optimizing the path, the system operates the motors of the jetbot to drive along the selected path. When beginning, the system uses the overhead camera bot to capture an image of the map and the jetbot. This image is calibrated and used by the AprilTag subprogram to identify the location and orientation of the jetbot in world coordinates. AprilTag uses the QR-like tag on top of the jetbot to assign it a unique identifier and associate the orientation of the tag to the jetbot. The camera calibration, computer networking and communication, and AprilTag process of this subprogram was developed during Lab 3.
The position and orientation of the jetbot is passed to the path planning subprogram developed using MATLAB in Lab 3. The program takes in the camera bot image and defines the boundaries of the road before populating the road with nodes and determining the optimal path from node to node to drive to the end location. For each node, the program outputs the heading angle between the jetbot and the node. If the heading angle isn't straight ahead, the system passes the angle to the reverse kinematics subprogram, outputting the appropriate motor values to turn. These motor values are used by the basic control subprogram to operate the jetbot's motors and turn itself. The reverse kinematics and basic control subprograms were developed in Lab 1 of the UAV module.
When the jetbot is facing the next node, the system activates the path-following subprogram, developed during Lab 2. This subprogram takes in the image from the jetbot camera and processes it to identify the center line of the road. The subprogram outputs a heading angle between the center of the image and the center of the road. This heading angle is passed to the reverse kinematics subprogram, as previously discussed. Once more, the basic control subprogram uses the motor values received from the reverse kinematics to move the robot forward and keep it on track with the center line. This subprogram continues until the jetbot reaches the location of the next node. At this point, the process is repeated as it moves to the new next node until reaching the end location and stopping. Simultaneously to this control program, the jetbot runs a sign recognition model to activate a flag if a road sign like a stop sign is identified. If the system detects a stop sign, the normal control program is interrupted and the robot stops for a safe period of time. Similar interrupts are performed when other signs, such as a one-way or parking sign, are identified.
The team decided to combine 2 of the 6 objectives to achieve the final goal of crossing an intersection using kinematics and beginning to path follow around the perimeter of the track using line following. The team combined and modified the code developed in Labs 1 and 2 to execute both objectives in a single program. This process required the team to iterate the motor speeds and durations as well as the HSV values for the camera's ability to detect the center line. To improve the design of our final goal, further technology could be explored to improve the safety of the robot. Vehicle-to-vehicle, V2V, communication is a type of technology that was not investigated in the lab setting and allows vehicles to wirelessly communicate about their location, speed, and heading. Having this software implemented in the robot could help to better determine crash threats and allow for multiple teams to complete their desired objectives in the same location and time frame.
Oh, sorry. Purpose of this control to start the line function.
While the team's experience with autonomous vehicles is on a smaller scale than in industry, the concepts used are equally applicable when designing full-size UAVs and in other mechanical engineering applications. The process of connecting each concept in the flowchart helped to create an ideal implementation of UAV technology, while the team-defined subtask allowed for a real-world implementation of a shorter subset of the program. The combination of these exercises utilized skills learned in the classroom and results in a thorough and well-rounded understanding of the principal concepts behind UAVs.